Hopefully I am audible. Yeah, great. So it is really good to see the crowd gets thinner with time. I mean, that is something we'll also discuss today, the black hole perturbation theory. Whenever you perturb a black hole, with time it decreases exponentially, of course. It's time to see what happens in this course. If it is exponential, by the end of the day, there should be only one left, maybe Dawood and the organizers. Let's see how that works out. So as I said, what we have finished doing in the last lecture was to derive the equations that a massless and a massive particle sort of satisfies when it moves on a Schwarzschild background, or in general any static spherically symmetric background. So I will just rewrite those equations in case I mean you have already forgotten. So dr d tau whole square was found to be g over f into e square minus f into 1 plus L square over R square. This was for the case of massive particle, and we also obtain this result that this is g over f e square into L square by R square. This is for the case of massless, right? So we had already discussed the case of massive particle to some detail, in the sense determining the perihelion precision for a massive particle. So it is now time to take up the case of massless particle. Okay. So this talk, which I will be this 1.5 hours or so, whatever is left, we'll discuss massless particles together. I have just written the massive particle because of a particular limit which we wish to discuss at some stage of our lecture, and so that's why the massive one is there. For the massless case, and in addition, we also have this relation, which is d phi d tau is L over R square, right? So we'll have in the massless case, and let us work exclusively with Schwarzschild for the moment being, and then we'll see for the general case also what happens. So therefore, if we concentrate on Schwarzschild, then we have the equation as dr d phi whole square, which is R4 over L square e square minus 2m over R into L square over R square. So dr d phi whole square corresponds to dr d tau whole square divided by d phi d tau whole square. D phi d tau whole square inverse will give me R4 divided by L square, and dr d tau is the same. G is equal to f because as I am specifying to Schwarzschild metric, and f is 1 minus 2m by R because again of Schwarzschild, and the rest of it remains the same, which if I convert to our beloved u coordinate, so u equals to 1 by R, then I will have this very simple looking equation du d phi equals to e over L whole square minus by R into L square over R square. And if I change now R to u, what I will have is, instead of this, I will have 2mu L square. Sorry, it would not be any L square because L square would have been cancelled. So there is L square over there, there is 1 over L square, so this 2 L square will cancel, and this is the final result that you will have. Right? Clear? Okay. Now this L over E, which is the ratio coming over there, let us try to find out what is the dimension of this quantity E over L. So dimension of energy is what? mv square, half mv square. So m L square t to the minus 2, right? Now L is same as t because c is 1, so dimension of energy is that of mass, and mass is same as length. but angular momentum has a dimension mvr, which corresponds to m L square T inverse. L is equal to T, so it is mass into length. So therefore E over L has a dimension of inverse of length, correct, or L over E has a dimension of length, correct. So given that L over E is what people denotes as B in this context, and this B is defined as the impact parameter. Okay. So why it is called as impact parameter is that L and E, these are both conserved quantities. So suppose you have a situation where there is an object here and say some light ray is passing through it and hence bending. So then this distance is what you refer to as the impact parameter to that system, which is B, right. Now at that point, what is the angular momentum of that object? The angular momentum is effectively the momentum times B, because B is the distance from here. And what is the energy? Since it is light, so E is equal to P into C, massless particle. So that means energy is same as momentum. So L over E is momentum into B divided by momentum. So that means L by E is actually related, which is called the impact parameter. So therefore, in the case of massless particle, you will often find that this relation will be written as 1 by B square 1 minus 2mu into u square. So this is the form of the equation which is used, and what the easier way of solving it is to take one more derivative of the equation. So if with respect to phi, if you take one more derivative, what do you get? You get 2 du d phi into d2u d phi square. Derivative of 1 by b gives you 0 because b is a constant. Derivative of u square gives you 2u du d phi. So 2 du d phi can be cancelled from both sides. Derivative of u cube will give you a factor of 3. That means you will get a 3 by 2, which cancels this 2. So you will get a 3m into u square. So the equation will be d2u d phi 2 plus u equal to 3m u square. So this is the equation which you have to solve for. So as you notice, the term on the left hand side comes because of you have a massive particle. If you do not have any mass which is present, then there is nothing on the right hand side. Then the equation is simply d2u d phi 2 plus u equal to 0, right. And what is the solution of that equation? Yes, so u is equal to some constant into cos phi, right, right, and 1 by r equal to a cos phi is the equation of a whose equation this is? Straight line, right. You could have made it even if you do not know, because if there is no gravity, a massless particle is going to move in straight line, right. I mean, come on, there is no force, so there cannot be any deflection, it has to move on straight line. So this is the equation of a straight line. You can verify that later on that this is indeed represents a straight line. Why it is a straight line and why things look different is that this is the straight line, right, but your origin is here and you are saying that this is my coordinate phi. So then you see when it is at infinity, then what is your phi? I mean, actually I should say this is phi, not that. So then what is phi? Phi is pi by 2 and cos pi by 2 is 0, which means it is infinity. Similarly, if it goes there, then your phi is minus pi by 2, that is also 0, that is also r equal to infinity. And only at this point your phi is equal to 0, so your a is actually the impact parameter, because impact parameter is this distance. So that means the leading order contribution will be 1 by r equal to 1 by b cos phi, right. Now I have a correction which is 3mu square due to the gravitational field, and as a consequence the trajectory will no longer be straight line, and if it is not straight line it is going to be some curved line, and as a consequence there would be bending of light, as simple as that, right? Yeah. So in that case what happens is that the same diagram gets modified to the following. So you have an object over there, and assuming, I mean, it's a very much exaggerated picture, but you know, I mean, just for the sake of it. So this would be the original direction in which the photon or the massless particle would have traveled if there were no mass which is present. But now due to the deflection or due to the modification, this is the new trajectory, and that means I have a deflection which has happened, which is this angle delta phi. So it was supposed to go straight if there is no gravity. Since there is gravity, it has moved along this angle. So this is the deflection which has happened due to presence of this mass over there. So this is my mass m. So the job is to compute what is delta phi, right? Clear? Now let us see how to do that. As I said, you do it by perturbative method. So you say it is 1 by b cos phi plus some v. Okay, and you assume that v is a small quantity because the deviation is assumed to be small. Correct? This I can always do. So if I substitute it back there, the 1 by b cos phi, its double derivative plus u is going to give me 0, because 1 by b cos phi exactly satisfies this equation d2u d phi 2 plus u equal to 0. So that means I will get the following differential equation, which is d2v d phi 2 plus v equal to 3m by b square cos square. I should get 3m square of u. If I square it, first term would be 1 by b square cos square phi, second term would be linear in v, and the third term would be v square. As I said, I will be working only at a leading order, so that I am only keeping terms which are coming over there, but I am not keeping terms of v which are coming on the other side. This is an approximation. So therefore, I should of course put an approximation symbol over there. Okay, there is a question that you should ask and you should tell me tomorrow what is your answer. Is that this is a term which is linear in v. If I square it, I should also get a term linear in v, but it would be multiplied with v cos phi and things like that. So that is the reason why I have not kept that term. I mean, I will tell you the reason even now, because cos phi, you see, when I am talking about deflection, it is mostly happening in this region. So there cos phi is always a quantity which is smaller than unity, because that's where the deflection is present. So therefore you have a smaller than unity quantity multiplying v, and secondly b which is present over there, that can be large, like the particle is coming from a large distance. So if b is large, then this ratio is further suppressed compared to this term v which is only present over there. So that is why I have not kept terms which is linear in v in the second order, I mean in the next order term over there, just kept up to this. This equation fortunately can have an exact solution. So what is the exact solution? Any guess? So let us try it out. I mean, you should be able to guess it by just looking at it. So the solution is a plus b cos square phi. We'll determine what is a and b, but this is the answer which solves this equation. You can see, because v is cos square phi, if you take double derivative of it, you will see a similar term will come, because dv d phi is what? This is twice v right. correct, which is minus b sine 2 phi. And what is another derivative of sine 2 phi? Cos 2 phi. And what is cos 2 phi? 2 cos square phi minus 1. So again you get cos square phi. And the constant you can always adjust by choosing your a appropriately. So therefore your d2v d phi 2 is equal to minus 2v into 2 cos square phi minus 1. Correct? Cos 2 phi is 2 cos square phi minus 1. At least that you should agree. Then if you substitute it back, you get 2v minus 4v cos square phi plus a plus b cos square phi is 3m by b square phi. Now this equation will only make sense if a plus 2b is 0 and b is equal to minus m by b square. So you see what is the coefficient of cos square phi? Minus 3b. So minus 3b should be same as 3m over b square. So b should be minus m over b square, and this is 2b and this is a, so they must sum up to 0 because right hand side has no term which is constant. So this determines for you capital A, which is 2m by b square. That means the general solution to this equation will be u equal to 1 by b cos phi plus 2m by b square minus m by b square cos square phi. So this is the solution. This is the solution for u that you will. So let me tell you what are the approximations involved. So this v I have ignored over here, that is the approximation, but rest of it is an exact. So this v equal to a plus b cos square phi is an exact solution of this differential equation, and that I have simply substituted over there. Is that clear? Any question? Now you see, originally when phi becomes pi by 2, then your u was, look at this solution over there. When phi is pi by 2, then what happens? R is infinity. But now when phi becomes pi by 2, then R is not infinity. Correct? So that difference that you have from pi by 2 is what corresponds to your bending angle. If there was no gravity, it would have been pi by 2 would make u equal to 0. But now because there is gravity, there is a bending. So even if you put u equal to 0, which means you have reached infinity, your phi will no longer be pi by 2. But there would be pi by 2 plus a small amount which will remain, and that is what you want to find out. Right? Makes sense to everybody? So I need to solve for this equation with setting u equal to 0. Right? Clear? So if I do that, what do I get? I get a quadratic equation which is m by b square cos square phi minus 1 by b cos phi minus 2m by b square equal to 0, and the solution is cos phi equal to minus b plus minus square root b square plus 8 by b square by 2m by b. Let us see if it is correct. See, you can multiply the whole thing by b, because this is 1 by b square, this is 1 by b, this is 1 by b square. So therefore this will be minus 1. So that gives you 1. Then this b square is 1. And then 4 times this 2 multiplication, which gives you 8. And then you have here 2m over b. Right? Fine. Then what you do, you expand it out. You do not take the so let me expand it out anyway. So I will get 1, because m over b is again a small number, as I discussed, because m is related to the mass of the black hole, which gives you a length scale of about few kilometer, but b is much larger, which is the impact parameter. So b, which is this one, so that is much larger compared to the typical size. So therefore I can expand this in powers of m over b, right? So that gives me 1 plus 4 m square over b square with a minus, then 2 m over b. Now the plus sign, if you consider, then you realize that the leading order term is b over 2m, which is a very large number. Correct? But that cannot be, because cos phi is supposed to be a small object, so it cannot be that large number. So you must take the other sign, which is minus. Now if you take the minus sign, this turns out to be 2m over p. Right? So choosing, if you want, is correct. Sure, sure. I will tell you why. So let me answer your question. So you see, when I got this, right? So when you solve this equation, there are generally two solutions. One which comes from this solution, which is the homogeneous part of the differential equation, and the other one is what is called the particular solution. What I did here is the particular solution, so there are no initial condition or arbitrary constants which is appearing. Now the solution of this equation is again in terms of cos phi and sin phi. So that is already present over there. So that's why there is no need to again solve it. What we are needing is just the particular solution. Now here when I am solving this, the part without 3mu square, in principle I should have sin phi and cos phi, but then the fact that it has to be straight line, that actually forces me to choose one of the solution and not the other. Pardon? Yeah, there can be a fine, clear. Now as I said, the phi has to be pi by 2 plus or minus some delta phi. Now you see there are two things. One is a deflection which happens at that end, look at this diagram, at that end, and another which happens at the other end, because both are u tending to infinity, sorry, u tending to 0. So what happens is that the actual delta phi would be twice of that value. You can think of that this is one deflection and then this is due to another deflection, and the total would be twice of the deflection due to both of them, because this cos phi can be phi plus pi by 2 plus delta phi or pi by 2 minus delta phi, depending on the sign. So whatever you get from here, the twice of that value, the delta phi, would be your deflection angle. Right? Clear? So then if you write it as cos of pi by 2 plus delta phi, actually this would be delta phi by 2 as 2m over b. Then cos of pi by 2 plus delta phi by 2 is minus sin delta phi by 2, and sin x you can approximate as x when x is small, delta phi is small. So given that, you will obtain that delta phi is 4m over b. So this is the result for the bending angle of light with this famous factor of 4. and if you include g, it should be 4gm by b or 4gm by c square into b, whatever you prefer, right? Now let me comment on the Newtonian result. I mean, how can you get that 2m over b result? So for that, you have to go back to the case of massive particle, okay, and study the Newtonian limit of that equation. So you see, in this particular case, as I mentioned, okay, I think that has been erased, but still let me do it here. So you had this relation, if you remember, du d phi whole square was something like e square minus 1 over L square. Then there was this 2mu and u square, maybe this was plus, this was minus, and then there was this term which is 2mu cube with a minus, and as we argued that this 2mu cube is the term which is coming from the general relativistic correction. In the Newtonian case, I would just have these two terms which are present. So therefore, I am doing Newtonian gravity, so I will get rid of that term. I will take derivative of du d phi just like we did over here. Here from du d phi whole square we obtain the second order differential equation. If I do the same, then I will get d2u d phi 2 plus u is actually equal to m, I think this was L square. So this is what we will get. So this result I think was there in one of my the previous classes notebook. You can just look it up over there. And because if you take one, this if you, I have taken to the other side, which is this u. This derivative, the 2 will be cancelled because there would be a 2 du d phi cancellation throughout. The square will remain. So now you compare these two equations. Here I had d2u d phi square plus u equal to 3mu square. Here inside I have simply m over L square. Now this equation you can again solve by exactly the same technique, and the solution you already know. The solution is m over L square plus 1 by b cos phi. You just substitute it here. I mean, it should be very much trivial to check that this indeed satisfies the differential equation, right? Now you ask the same question, what happens when u goes to infinity? You get a solution for cos phi, and what is that solution? mb by L square. Correct? You are just solving u equal to 0, which is r equal to infinity. Just compare. Here what we did, we had this as the where is that? There. We had this as the most general solution, I mean with that approximation which is involved, and then we said that let us put u equal to 0 and solve for cos phi, which we did, and obtain minus 2m over b. Here also we are solving exactly the same equation, I mean a different equation, but the nature remains by b cos phi, and the solution is cos phi equal to minus mb by L square. You just compare it with the solution that we opted, right? So you notice that except for this L and B, which we will come back to, there is a factor of 2 which is present here, but there is 2 which is there. As a consequence, when you do exactly the same thing, that is you change phi to pi by 2 plus delta phi by 2, the deflection angle will turn out to be 2mb over L square instead of 4mb over L square, right? Makes sense, everyone? Okay. Now what is the relation between A and B? As you know, is equal to the momentum mv times r, right? Now this is a massive particle, So therefore it must have some velocity at infinity. So therefore L will be, actually L is per unit mass, so this would be velocity at infinity times B, because B is my impact parameter, which is my R, and V infinity is my speed. So therefore it should be V infinity times B. So I plug in that value of L over there. What do I get? I get 2m by B into 1 by V infinity square. V infinity very close to that of C, since it's a high particle. Then this will be 1. You will get a result which is 2m over B, while here you have a result which is 4m over B. So this is the famous factor of 2 that you get in the bending angle of light in the relativistic calculation versus the Newtonian calculation, where you get a factor of 2, here you get a factor of 4. Does that make sense? Right? Now, there is one historical remark which I would like to make, and that tells you that everyone makes mistake. So I don't know if you already know this. So when Einstein first wrote this paper on bending of light in 1914, just after giving his theory of relativity, he actually got 2m over B. He did not got 4m over B. And at the same time, there was some German expedition which was planned because there was a solar eclipse in 1914, and that supposed to be testing the prediction that Einstein had. But as you know, historically, exactly at that time, the World War I broke out, and as a consequence, the German expedition was cancelled. And Einstein later on, in a later paper, he realized that this was a mistake that he did. It should not be 2, but rather it should be 4m over B, which was later confirmed by Eddington. So therefore you realize that if that German expedition had happened, if World War I had not had happened, then Einstein would have been proven wrong, that it's actually 4 times than 2 times than what Einstein predicted, and then the history could have been different. It could have been that experiment will tell how theory is going to shape up and things like that. But thanks to World War I, we theoretical physicists are very happy that Einstein actually found that 4 factor first, then 2. So anyway, with all those fun keeping aside, let us move on. Yes. Yes. Mm-hmm. But what do you mean by other matter? But that would be very less probabilistic, right? Yeah, but people do something else which I will come back to as your question to dark matter, which is somewhat related to this. Okay, so any other question? Okay, actually the fact that delta phi has a 1 over B fall off has some interesting consequences which I will discuss now. So I will remove this part because this is not required. Now, due to this fact that the light gets bent, can you tell me where else do you see such phenomena? Huh? Yeah, diffraction, but even more when light moves through a material, right? Then there can be reflection, refraction, and light does bend. Okay, we are talking here about purely geometrical thing, not wavy nature of light. So let us not go to refraction, but it will be important for other cases, but not light. So therefore, for reflection and refraction, you will have bending. Like in the case of refraction, the light comes in, then it gets bent depending on the refractive index. So this suggests that even for light which is moving in curved space-time, you can actually represent it as if light is moving through a material medium with some refractive index. Now how that is done? So that is done using the following trick for static spherically symmetric metric. So you see your ds square is 1 minus, let me skip the g, 2m by r dt square plus dr square by 1 minus 2m by r plus r square d omega square, right? This is the metric that you have, so, which you can rewrite as okay, let us make it r. Okay. So if you can write it in this form, this is known as the isotropic form. Isotropic because the 3 metric is purely flat, dr square plus r square d omega square. Now how do you determine this quantity h of r? There would be two equations. So there are two things to determine: how capital R is related to small r, and second, how h of r is related to 1 minus 2m over r. So first thing you notice is that your r square must be equal to hr into r square. This comes from equating the coefficient of d omega square in this metric, which is r square, to the coefficient of d omega square in this metric, which is r square into h of r, right? Now whenever you have this relation, you see get dr to be equal to, or maybe r dr to be equal to h prime r square into dr plus h into 2r dr. So from there you get a relation that dr is equal to, or 1 over 2r dh dr r square plus capital R by small r into h. So this is a relation relating small r to capital R. You just take a derivative of that and you get what is the relation between d small r by d capital R. But you also get the same relation by relating dr square by 1 minus 2m by r with hr into dr square. They should also match with each other. So that means you also have this result, that is dr over dr should be square root h of r into 1 minus 2m. So equating these two, you see that you get a differential equation for h, which you can in principle solve. For Schwarzschild metric, this differential equation can be exactly solved, which I will not do here. You can just type in Google isotropic coordinate for Schwarzschild metric. It will immediately tell you the answer. But the point that we are interested in, as I mentioned, is in the weak field limit. So in the weak field limit, you can actually show that your h of r is nothing but 1 plus 2m over r. In the weak field limit. In generic, it will have a different expression, like it was, I think, 1 plus 4m by r and then 1 minus 4m by r, some ratio is present. I mean, if we just keep terms up to linear order in m over r, you get 1 plus 2 m over r. Fine? Clear? Now, having obtained a metric in this form, that is where the next game begins. So you see, what is the equation for a light ray's trajectory? ds square equal to 0, right? So if I put ds square equal to 0, this equation tells me that 1 minus 2m, let us keep it capital R, dt square plus 1 plus 2m by capital R into dl square is 0, where dl square corresponds to dr square plus r square d omega square, which is my 3-dimensional line element. Correct? If this is 0, I can immediately compute what is the effective velocity, which is dl dt. That is the effective velocity. If you do it in that, you will get minus dt square plus dr square or dl square, which means dl dt equal to 1. It moves. But now the coefficient of dt and coefficient of dl are 1, and the speed would be dl by dt, which is given by 1 minus 2m by r divided by 1 plus m minus 4m. So you see the effective velocity is smaller than that of light, that of 1, which is expected, and the smallness is by this factor 4m over r. And it's quite coincident that this is exactly same as reflection angle, which is also 4m divided by b, and this is 4m divided by r. Here, yeah, I did not change it. What I simply did was to say that solution of this equation at leading order is r equal to capital R plus order m over r. If you solve it, then you see when you are putting it here, then the next order term would be order m square over r square, which is higher order term, so I am ignoring it. So at leading order you can replace small r with capital R. So that is all that I have done. I have replaced small r with capital R and over here. Right. So that means the refractive index n would be C divided by V effective, which will be 1 plus, oh, I think I made a mistake here, it should be square root, and then it should be 2m. Yeah, see, it was dl square and dt square, right? When I am computing dl dt, there should be a square root, and this would be 1 plus 2m. So this is the effective refractive index of Schwarzschild spacetime. So that means when you are thinking of propagation of light, you can forget about gravity, and you can just think that this is like the light is moving in a medium with a refractive index which depends on the location, because the refractive index depends on r, one of the radial coordinate. So it is not a homogeneous medium. For homogeneous medium, refractive index would be same at every point. This is like a medium where refractive index changes with your radial distance. If you go to infinity, then your refractive index is 1, and if you go to at r equal to 0, your refractive index is very high, or so on, which means as you probe deeper and deeper, your light is facing more and more obstruction. That means it will bend more effectively, and that is something which is expected, because as you go to lower radii, you are going to higher and higher gravitational field, which means the deflection is going to be larger. Right? Clear? Fine? Okay. Now you ask the question that suppose here, and there is, my friend is over there, I am sending a light to my friend and it is coming back to me. Normally what time it would have taken? It would have taken simply the path difference between me and my friend. But now the light is moving through a medium with a refractive index, so there would be an additional time delay. Or in other words, suppose I know that I am at a radius 10 kilometer, my friend is at a radius 20 kilometer, I would have expected the light travel time for 10 kilometer, I mean 20 kilometer, because it has to go from 10 to 20 and come back to me. But now because there is a varying refractive index, I will have a different estimation for the light travel, and that time delta t will correspond to twice integral n dl, or in this case n dr, from r1 to r2 minus twice r2 minus r1. And this object delta t is what is known as the Shapiro time delay, and this is something that you can measure. And because, for example, suppose there is a spacecraft which is flying, then from Earth you can send a signal to that spacecraft, and as soon as the spacecraft receives the signal, it again sends another signal back to you. So then this is exactly, you will see that it's not what you would have expected if you were in flat space. It is as if you are immersed in a Schwarzschild background. So that will be another test of GR, right? Because if it is because you know the mass of the sun, so you know what should be the time delay. And if it is different, you will say that, well, maybe there is something more in the space time. It is not exactly given by the mass of the system. This integral you can easily do because it is 1 over r. And what is integration of 1 over r? Is a log. So that means the time delay would be 4m log of, say, r by some scale. Let us put it r naught. Okay. So this log term is very characteristics of GR of a point mass. If you have, for example, a charge which is present, as we discussed in the previous lecture, that if you have a charge instead of 1 minus 2m by r, if you had a q over r square, then what you will find is that this will have a correction of order q over r square, and this if you integrate, you will also get a correction of order q by r, which is a very different behavior with radius than the log. So that means even by understanding how the time delay falls off with your radius, you can actually tell whether there is a only GR or whether there are additional corrections to your metric, because the fall offs are completely different, right? Clear? Now, before finishing this, let me very briefly comment on this log term which is here. So, some of you may be familiar about gravitational lensing of gravitational waves, which is a very important topic nowadays, where you have a small mass and gravitational wave is coming, it interacts with it and then it gets lensed. Just like, you know, if you have a lens, you can see things bigger and smaller. Similarly, the gravitational wave strength can be enhanced, magnified using this lens. There also what people use is what is called a lensing potential, and that lensing potential is exactly this, which is 4m log of r. And the fact that this log is extremely important because of the log, the amplification is substantiable. If you have a 1 over r fall off, that's something that we had seen recently, then the time delay and hence the effect to the gravitational lensing is extremely small, and in particular there is very little chance of detecting it in any near future. So that actually keeps this log term a very specific thing, because even if your r is very large, your 1 by r is going to fall off like anything, but your log r will still be an appreciable number to work with. So that is why this log term is very important. Okay, so if you have any chance to work on gravitational lensing, you will encounter this log term over and over again. This is called the gravitational lensing potential of a point mass lens, which is typically always used. So any question up to this point, then I will go over to the next. Yes, we have to. Yes, yes. Right way of doing things. Yeah, so this is a three-dimensional length. That is why we use this isotropic coordinate. I mean, even when people do lensing, you will find they will only use isotropic coordinate in this case. So that is actually some caveat in the standard lensing literature, because see here, for example, you can see this is minus and this is plus. But if you add a charge, for example, such a correspondence will break down, and that will have other consequences and so on and so forth. So you should not take everything at face value. Okay, there are many books which will say this equation holds for gravitational lensing of gravitational waves, but they're actually wrong, because isotropic coordinate, unlike here where your GTT and GRR are same, that is not true in isotropic coordinate. So you have to be careful. Okay, fine. Very good. If there is no question, then fine. Should I proceed? Then the next most important thing in this analysis. So this is no longer required, so I will remove all of it. Is the photon sphere. So that is where we are going close to that of a black hole. So what is a photon sphere? So photon sphere corresponds to the radius at which the photons move in circular orbits. So for that, what we need to find out is how to determine the location of circular orbits from the equation that we have above. Now can you tell me how do you determine circular orbits in Keplerian geometry? What was the idea? Huh? Correct. Because if it has to be circular, that means it either has to be at the minima of the potential or at the maxima of the potential. We only have these two possibilities. Sorry. So therefore here, as we know that this is my effective potential. Right? All of you agree? So that means I have to take derivative of this effective potential and set it to 0. But in addition, if an orbit is circular, then dr d phi should also be 0, because if phi is changing, my r cannot change. Right? So then I have two conditions. One, dr d phi should be 0, which means I have a relation which says that E square over L square should be 1 by r square into 1 minus 2m by r. It just follows from here. You set dr d phi equal to 0, then the quantity inside square bracket must vanish, and you should have E square over L square to be 1 by r square into 1 minus 2m by r. Second condition is dv effective dr equal to 0. Now if you do that, what do you get? First I have to take derivative of this, which gives me 2m over r square. So I get 2m over r square into L square over r square. Then I have 1 minus 2m over r times 2L square over r cube equal to 0, which is the derivative of L square over r square. So can you solve this equation and tell me what is r? Yes, yes. So this would be 3. So that means I can no longer ignore m over r, because m over r is 1/3, which is a appreciable number, not very small. So I have come from a large distance to 3m, and I want to see what happens to 3. Right? So that means there is only one solution. So there is only one radius at which it happens. So we need to determine whether it's a maxima or minima. Right? Because it's a one solution. So then to obtain whether it's a maxima or minima, you have to take another derivative, which you can do at your home. I will not do it here, and you will find that this is a maxima. And since this is a maxima, it means that photon circular orbits are unstable. Because if something is at the top of a potential, if you perturb it by a small amount, it is either going to roll down on either of the side, and that means the photon sphere is unstable. The fact that photon sphere is unstable is extremely crucial for black holes to be stable. If photon sphere are stable, then you can prove that black holes are not stable, and vice versa. So if there is a minima in the photon sphere, then actually the black hole will not be stable, which is what we will come back to, but just after a few minutes. So this is fine, very good. Now what you can ask is that, so suppose I have, okay, I can draw it here. So suppose I have a black hole which is here, right, and there are light rays which are passing through. At large distance they will pass through unaffected, because its gravity is very weak, At somewhat smaller distance, there would be a deflection which is present. I am just drawing it in an exaggerated manner. There would be deflections which are present. Similarly, over here. But at some small distance, all of it is going to be absorbed into the black hole. And this radius from which all the light ray are going to be absorbed by the black hole, as you can see, is slightly larger than the size of the black hole itself, right. So, this particular thing is what is referred to as the black hole shadow, because if suppose you have a black hole and there is a background illumination, then normally it will cast a shadow. So, similarly here, if you have rays coming from these regions of that illumination, it is never going to reach you. So, therefore, when you are looking from here to a large distance, you will find that there is a region which is black, because light from that region is not reaching you. That radius is not 2m, because 2m is even smaller than 3m. So, if your r is less than 2m or 3m, then it is bound to go inside the horizon. But what I am saying, even if it is slightly larger than 3m, even then it can fall into the black hole because of the bending phenomena. So, what we need to compute is the absorption cross section of a black hole, is what is referred to in this context. So, how do you determine the absorption cross section of a black hole? You determine the impact parameter, the minimum impact parameter for which the particle can escape to infinity. If the impact parameter is smaller than that, then the particle will be captured by the black hole. If the impact parameter is larger than that, then the particle will anyway escape to infinity. So, I want a limiting or critical impact parameter at which it will barely pass through, right, makes sense. To do that, let me draw the potential. So, normally the potential will be of this form. So, this is my r equal to 3m, this is r tending to infinity, and this is r tending to, this is a bad way of saying. So, at r equal to 2m, you can see the effective potential vanishes, because it is 1 minus 2m by r. At r equal to infinity also, the effective potential vanishes because of 1 by r square. So, at 2m as well as the infinity, the effective potential is 0. Only at r equal to 3m, the potential has a maximum, right, fine. So, now suppose there is a particle which is coming in, whose energy is smaller than the maxima of the potential. Then what happens? It will hit the potential and go to infinity, correct. But suppose there is a particle which is coming like this, whose energy is larger than the maxima of potential, it will just fall into the black hole, correct. So, the limiting case corresponds to the situation where energy is exactly equal to the maxima of the potential. See, your impact parameter depends on what? L divided by E, correct. So, that means impact parameter's critical value is related to critical value of energy. So, that means if I have an energy which is smaller than the maxima, it will go to infinity. If I have energy which is larger than the maxima, it will fall into black hole. But if I have an energy which is exactly equal to the maxima, it just barely can escape or fall into the black hole. So, that is the radius that we want. So, therefore, here setting E equal to V effective at r equal to 3m. So, as I said, E is equal to maxima of the V effective. The maxima happens at r equal to 3m. So, I will put r equal to 3m over there. What I get? I get 1 minus 2/3 into L square over 3m square which means sorry, L by E whole square equal to B square equal to 3 into square. So therefore you see the critical impact parameter is not 3m, it is root 3 times 3m. So it is larger than 3m, which is what I sort of argued. Because of the bending, there would be rays which are above 3m, but they have to fall inside a black hole because of the strong gravitational field. So this defines for you the absorption cross section, which is pi into b square, which is 3 pi into 3m whole square, or this tells you this famous result that it is 27 pi. So this is the absorption cross section of a Schwarzschild black hole, and this is exactly what you will get in the context of shadow. For shadow, there are some parameterization which they use, which are alpha beta, because the shadow shape has to be spherical, but ultimately this all boils down to this particular absorption cross section which is present. If you now add, for example, a charge to your metric, like I said, it is 1 minus 2m by r, but suppose you add to it a q over r square, then the location of photon sphere is going to be changed, because this comes from derivative of 2m over r. Here you will have an additional term due to charge, here also there would be an additional term due to charge. The photon sphere is going to change, and if the photon sphere changes, the maxima at V effective at maxima is also going to change. The absorption cross section is also going to change. What you can show is that if you have a charge, then sigma absorption will become 27 pi m square times 1 minus, I think, 4 q by m square. So you see, if q is positive, which means you are dealing with a Reisner-Nordstrom black hole, then you find that the scattering absorption cross section is smaller compared to that of Schwarzschild, because it is Schwarzschild times 1 minus something, which is expected, because for Reisner-Nordstrom black hole, there is electrostatic repulsion kind of a thing, so therefore the gravity is slightly weaker, and as a consequence the absorption cross section decreases. On the other hand, if q is negative, then your absorption cross section increases. So that means, suppose you could measure the mass of the central supermassive black hole Sagittarius A star or M87 star, for both of which we have seen the black hole shadow, then you know what is your prediction for sigma absorption. If you see your shadow size to be larger than what is expected, then that could be due to presence of a negative q, because that increases the absorption cross section. Or if you see that the shadow size is smaller compared to what you have expected, that could mean that you have a positive q corresponding to either Reisner-Nordstrom or maybe scalar here or some of the other theories. So this can be a telltale signature for theories beyond GR using shadow. Right? So the calculations are simple, you just have to do it in this particular way. For Kerr black hole also the result goes in a similar way. It is just that there would be two such solutions, and there are no photon sphere, there are only photon region, so to speak, because of the orbits may not close and so on and so forth. So there is Pandora's box associated with Kerr black hole's photon region, which I will not get into, but for Schwarzschild it's a nice and good spherical region around 2m where the photons just move in circles. And if you slightly perturb that photon, it simply either goes into the black hole or goes to infinity. Is this clear? Okay. Any confusion, question? Okay. So I have 15 minutes. So yes. Yes. B equal to 3 root 3m. Yeah. no, pi times b square. So it's like you are looking there, there is a spherical region of radius b. So its area is pi times b square. It's just the area of it. Yes, absolutely. Which you can compute, by the way, by the same argument. So you start with the V effective, you determine whether it has a maxima minima for massive particle. So in whatever you do, there will always be a maxima, but for massive particle, for some choices of angular momentum, you can also have a minima which is present. So for example, a typical plot would be something like that. Okay, so this is where your circular orbit are located, stable circular orbit. And you remember we discussed about this perihelion and aphelion, they would correspond to this type of a slice. This would correspond to one of them, perihelion, and this would correspond to the aphelion or vice versa. And so this would be the bound orbits. Then there can be scattering orbits which are like this, and then there can be orbits which falls into a black hole, which would be over there. So you can play exactly the same game as we did for the case of photon, for the case of massive particle, and obtain the absorption cross section. Right, but the problem is, I mean, massive particles, I mean, what are the massive particles that you can see? Electrons, possibly, or protons, but since they are mostly charged, they will not reach you. I mean, you can only see the massless particles coming towards you. That is why you only see shadows for massless particles. Right. See, this is done under the assumption of q by m square being small. So therefore, it can never be 1. If you do it in general, it is difficult because I mean, this will give you a quadratic equation and so on and so forth. So there can be some curious situation. For example, if in the horizon, there is something called the naked singularity. So if your q is same as m square, then there is no horizon. The horizon just goes away. So you can have similar situation here also, where this can be set to 0 for some choices of q, but generally they are very high, which means they are highly non-perturbative, and we do not, I should not say they cannot exist because that would be too strong statement, but the general belief is whatever be the correction to gr, they should be small. So that is why, I mean, we assume that generally these terms are small, and hence this will always be fine. Right, makes sense? Anything else? Okay, if not, then let me change my gear and discuss something else. Or maybe Daud, I can do it tomorrow probably, because I think the students might be very, because it's related to Q and M, so I think I will do it tomorrow, because that way I will have a continuity. So I think I will stop here and I will take it up in the next class. So if you have any question, you can tell me. Or so let me tell you what I have finished. I mean, just to summarize everything. So today we have mostly talked about weak field tests of gravity, which includes tests due to massive particle, namely perihelion precession, and also tests due to massless particle like bending angle of light. Then we move to a region close to that of black hole, which is r equal to 3m, and there we did another test, which is the shadow radius of a black hole, and we showed that it can vary depending on what is your background theory, what is your metric, and so on and so forth. Now, just as a prelude to my next class, so the point is, how do we say that whether it's a black hole or not? Because at this point, the metric we are more or less know, like how the corrections are going to happen and so on and so forth. So the more important question that comes is whether we are sure that the object that we are seeing is a black hole. Now, for black hole, first of all, if you have some object which is more compact than that of a black hole, that also have a photon sphere exactly at r equal to 3m, and therefore shadow can never be used to distinguish them, because you will just see a shadow at 3m, and even if it is a black hole, or even if it's an object which is compact than that of the photon sphere. So the question that you ask is, can there be stellar objects which are more compact than that of photon sphere? So the answer turns out to be yes. So those objects, there are some very exotic star which are called the Bugdal star, for which you can have a limiting radius, and that radius has a value which is I think 9 by 4 m. Okay. So therefore you see this radius is much smaller than 3m, because 3m would correspond to 9 by 3m. It is 9 by 4m, so it is slightly larger than that of 2m. So this is a star which is compact than that of photon sphere, but it is slightly bigger than that of the horizon. And this star can actually exist in our universe. I mean, at least our laws do not prevent them from existence. So if that star exists, then looking at shadow observation, there is no way to tell apart whether it's a black hole or it is a star which is as compact as that. So by seeing shadow, mentioning yes we have seen a black hole is an exaggerated statement. So shadow can tell you that whether you have seen a black hole or not. It can only tell you that you have seen an object which has a photon sphere located at r equal to 3m. That's all that you can say. Now whether it's a black hole or not, to say that you have to go to r equal to 2m, and that is what people would like to go, which you cannot do using your electromagnetic observation, because light most likely will not come out. I mean, there is a finite chance, but let us not get into that. The most prominent thing would be gravitational wave, which is going to come out and is going to carry information about r equal to 2m. And you will hear this phrase that quasi-normal modes are the key things and they capture the physics at the horizon. Again, in the next class I will prove that to be wrong, because quasi-normal modes, as we know, do not come from the horizon, they come from the photon sphere. So I will try to show you how photon sphere properties will tell you what are the quasi-normal modes of a black hole, at least in some approximation scheme where I can do analytical calculation. And then quasi-normal modes are also not a test of r equal to 2m or black hole, but there are other caveats and things like that which we will come back to. And that will bring me to alternatives of black hole, just like we discussed alternatives of gravity theory, and that will be the tomorrow's first lecture. Second lecture would be again going slightly away from black hole, which would be related to tides and so on and so forth. So but let us see how far we can. Okay, so if you have any question, you can ask me now or maybe later.